our last topic on waves is entitled stationary waves. We already mentioned stationary waves way back at the beginning when I told you about the different types of waves available. Your options were stationary or progressive. Those were one of the first options we had. So we're just going to focus on stationary waves because most of the waves we've been talking about thus far have been progressive. In fact, they all have been. And now we're going to look at this special case of stationary waves. So the way a stationary wave is most often formed is by the superposition of two progressive waves of the same frequency travelling in opposite directions, and this is most often achieved by superposing a reflected wave with its incident wave. A really common question in the exam is to explain how a stationary wave might be formed in a specific situation. Now it's often a wave that's been sent down a string, or a wave that's been made by a sound wave being sent to the bottom of a pipe, say like think a flute or a clarinet, or even just like a milk bottle kind of thing that's got a closed end. And it will always be that you say that the incident wave reflected at the end, it then superimposed with itself, so the incident wave superposes with the reflected wave, which causes areas of reinforcement and areas of cancellation, which form the bits of the wave that we're going to talk about in just a minute. But bear that in mind, that that will be what's coming. Right, I'm just going to get rid of my face, much to your delight, I'm sure, for this section, because it's quite a lot of diagrammy stuff and you needed the space. So the way we form a secondary wave. So let's consider I've got two waves, wave A and wave B, same amplitude, same frequency, same time period, but they're travelling in opposite directions. So at time 0, I've just put them next to each other here, wave A is going to the right, wave B is going to the left, and they are in the phase. So the peaks happen at the same time, troughs at the same time. So if I then put together the resultant of that, I find that I get reinforcement because I've got peaks at the same time and troughs at the same time. And I end up with a wave that has much higher peaks, much lower troughs, but has the same frequency and the same time period, but approximately twice the amplitude. Okay, so that's at time 0. So let's just roll on a little bit. If I roll on a little bit, quarter of a cycle later, so I'm now at time period by 4, so a quarter of the way forwards. They've both moved a quarter of a wavelength in opposite directions, so I've just tried to show that I've shifted them a quarter of a wavelength, not quite a full one, but a quarter of a wavelength. So that means now that my peak is lined up with a trough, peak, trough, peak, trough, peak, trough, peak, trough. So now I'm going to end up with cancellation. I'm going to end up with 0 amplitude. So I get absolutely nothing down the middle. So at time 0 I had reinforcement. Quarter of a cycle later I've got complete cancellation. So let's move on again. Let's move on another quarter of a cycle, so I'm halfway through the time period. They're both shifted again by a quarter of a wavelength, and now they've lined back up again. They're both back in phase, so I've got peak, trough, peak, trough. When I combine these together, I get reinforcement again, and I get this waveform that had twice the amplitude. If I go a quarter of a cycle later, again, I'll get cancellation. Quarter of a cycle later, I'm back to the beginning. Now, if I put all those waveforms on top of each other, it looks like that. So what you can see here is that there are points where these ends are, where no matter what point I am through the cycle, the displacement is 0 at every point. And there are points exactly halfway between each of these ends that I've labelled A, where I seem to get these maximum, these really big amplitudes, and it varies from being a positive to a negative amplitude, but I get a very big variation. So over time, if I looked at this point, doesn't matter what the time was, it wouldn't move. If I looked at this point here, over time, it would move from the top to the middle, to the bottom, to the middle. This one wouldn't move, this one would move all the way up here. If I look somewhere in between, I would find that it just moves same, so it would move at the same time as this one goes up and down, it just wouldn't move as high. Okay? I'm going to show you this on a string in the lab, and it will make a whole lot more sense then, but I just want to get into your head of what's going on. You should kind of have this visual. Even when I do this in real life with a string, it almost looks like this, because it moves so fast. Points that don't move, points that move a lot. Now these points we call, I just put them as N's and A's, but we call them nodes and antinodes. Nodes are the points where there is minimum, usually 0, amplitude. And the antinodes are the maximum amplitudes. And those are the key features of a stationary wave. So when I was talking earlier about how when I've reflected my two waves on each other, the incident wave superposes with a reflected wave, reinforcement causes the antinodes, the cancellation causes nodes. And that is how we form a stationary wave in most cases. Now, there are some specific types of stationary waves that we can form, and they have to match the thing that they are on. So if we think about a string, if I've got a string on a guitar, it's clamped at either end. So, can never get my hands on the camera. There we go. Clamped at either end, so it can't move. Can't go anywhere at all. So, if it can't move at either end, those 2 points have got to be nodes. So, any wave that I put on there has to be able to fit so that it would have a node on either end. Now if we just look back at how it was formed, if I just roll back to here, the distance between one node and the next, well, that has to be half a wavelength. Yeah, can you see how that must be half a wavelength? Because there's my full wave, so one node to the next node is half a wavelength. So if I'm saying on my string it has to be clamped to either end, so it has to be a node, then the biggest wave I could fit in there, or the lowest frequency, would be one that has a node at either end, which means it must have a single antinode in the middle. This is what we would call the fundamental mode, or the first harmonic. This would be the biggest wavelength or smallest frequency wave that would fit onto this string, where the length of the loop is equal to half a wavelength. Next one I could put on, so if I then start changing the frequency, I'll go through a point where I don't really have a proper standing wave until I hit this. This point where I've got node, antinode, node, antinode, node. Because it's closed at each end, I must have a node, so my second option that can fit on there would look like this. And this distance now, if you look, that's one wavelength. So the length of the string, the length of the 2 loops, must be equal to 1 wavelength. And that will be the second lowest frequency. So that's called my first overtone or second harmonic. And I can keep going with this. I could go up to a third one. Again, I've got to have one of these. I've got to end with a node because it's a string that's closed at either end. So it goes node, antinode, antinode, antinode. So now this distance is 3/2 wavelengths, and I can come up with a statement for the frequency of that wave. Oh, sure, it's covered up my writing. There we go. So this is for a string. But we don't just have strings, we also have pipes. So if I've got a pipe, the end that I blow into, that is an open end. So I always get antinodes at open ends of pipes. If I've got a closed end, I get a node. So I have slightly different options when it comes to pipe, depending on if it's got 2 open ends or 1 open and 1 closed end. So we'll have a look at those ones in class, but that's just something I wanted you to start thinking about. Okay, and that is it for waves. So if you've got any questions, make sure you ask when you see me, and shortly there will be a test upcoming because we've finished the topic. Yay! So excited, I'm sure you are. I know I'm looking forward to the marking. Okay guys, right, remember, any questions, ask when you see me.